Welcome back. This is part 4, the final one. We have built and scaled the core system. Now we cover everything that turns it into a real production system. Message queues, microservices, the patterns that keep it reliable. How it is shipped with containers and Kubernetes, and how we watch it and keep it secure. Let's finish this. Okay, when you place an order, several things need to happen. Save the order, charge the card, send a confirmation email, update the analytics, tell the warehouse. Now, some of that, like sending the email, is slow. And importantly, you, the user, do not need to wait for it. The email arriving 2 seconds later is completely fine. So, making the user wait for all of it would be silly. And the tool that fixes this is a message queue. A message queue at high level is a waiting line for tasks sitting between your services. Instead of doing the slow work right away, a service drops a little message, send this email into a queue, and immediately moves on and responds to the user. And separately, other programs called workers or consumers pull messages of that queue and actually do the work a little later. So the person who produces the work does not wait for it to be done. And this gives you three big benefits, all worth knowing by name. 1. Asynchronous processing. The user gets a fast response, and the slow work happens in the background. 2. Decoupling. The service adding to the queue and the worker reading from it do not need to know about each other or even be running at the same time. They only share the queue. And 3. Load leveling. If a sudden burst of orders come in, the queue simply hands them, and the workers work through them at a steady pace instead of everything collapsing at once. Now, a related idea. A plain queue usually has one message going to one worker, but sometimes you want one event to reach many different services. For example, order placed needs to reach the email service, the analytics service, and the warehouse service. That pattern is called publish subscribe or pub/sub. One event is published and many subscribers each receive it. And the famous tool here is Kafka. Kafka, at high level, is a durable log of events. Events get appended to named streams called topics, and many different consumers can each read through the log independently at their own pace. And here is the key difference from a plain queue. Reading a message does not remove it. The log just keeps growing, and each consumer simply remembers its own position in it. So, the email service can be at a position 900 while the analytics service is still at 500, reading the very same events without either affecting the other. Old events are dropped later by age, not by being read. That is why it is used for event streaming and data pipelines everywhere. And one important detail to get right, delivery guarantees. There are really three levels here, and you should know all three. At most once, a message is delivered 0 or 1 times, so it might get lost but never duplicated. At least once, it is never lost but might arrive twice, and this is the most common one. And where does the duplicate actually come from? At high level, the queue does not delete a message when a worker picks it up. It keeps it hidden from the other workers and waits for that worker to send back an acknowledgement, meaning done. And if that acknowledgement does not arrive in time, the worker crashed or the network dropped it, the queue assumes the work never happened and hands the message to another worker. So nothing is ever lost, but work that actually finished and simply failed to acknowledge gets done a second time. And at most once is just the opposite order. Acknowledge first, then do the work. So a crash loses it instead. And exactly once, delivered precisely one time, which is the ideal but genuinely hard. So in practice, it is usually faked by using at least once plus idempotency, so that a duplicate does not harm. So, because most systems are at least once, your workers must be able to handle the same message twice without doing damage. For example, not sending two emails or not charging twice. That safety property is called idempotency, and we will come back to it shortly. And if a message keeps failing, it gets moved aside into a special dead letter queue, so it does not block everything else. So, in our store, message queues let checkout feel instant, while the emails, receipts, analytics happen quietly in the background. Now, so far, our whole store has been one big program, but at a certain size, teams break that one program into many smaller ones. And why they do that and what it costs is the thing people get wrong more than almost anything else. Microservices. Okay, so far our entire store is one big program. All the code, orders, payments, products in one place. We call that a monolith. And honestly, a monolith is great when you are small. Everything is simple in one place, easy to run. But as the company grows to hundreds of engineers, that one program becomes a problem. So many teams are all editing the same code, getting in each other's way, and every tiny change means redeploying the whole thing. So the fix is microservices. You break one big program into many small independent services, each owning one area of the business. An order service, a payment service, an inventory service, each with its own code, its own team, and often its own database. Now, the most important point here, and the one people genuinely get wrong, the main reason to do this is not performance. And this one really does matter in a few interviews. Saying, I would use microservices because they scale better is one of the quickest ways to sound junior because it is not why companies actually split. It is about people and teams. With microservices, each small team owns its service and can build, test, and deploy it independently without coordinating with everyone else. That is the real win. Independent teams, independent deployments. And there is a second benefit, fault isolation. Because the services are separate, if the search service crashes, the checkout service keeps working. The failure is contained. But, and you must say this in an interview or you will sound naive, microservices are not free and not always the right choice. Splitting into many services means they now talk over the network, which is slower and can fail. Keeping data consistent across services is genuinely hard because you lose those easy single database transactions and the patterns to handle that, which are worth being able to name, are things like the saga pattern or two-phase commit. And briefly, the saga pattern means you do the steps one after another, each in its own service, and if a later step fails, you run a compensating step to undo the earlier ones. So, refund the payment instead of rolling back a transaction. Two-phase commit is a slitter one. A coordinator first asks every single service, are you ready? And only if all of them say yes, does it tell them commit. It is more correct, but it is slow. And if the coordinator dies, everyone is left waiting. And you now have hundreds of things to deploy, monitor, and debug. So the honest, senior advice is start with a monolith, keep it simple, and only split into microservices when the pain of one big codebase actually forces you to. And two supporting pieces you will hear about. First, with hundreds of services, the client should not talk to each one directly. So you put an API gateway in front, a single entry point that receives all requests and routes them to the right service, and also handles shared jobs like authentication and rate limiting in one place. And second, service discovery. Since services start, stop, and move around constantly, they need a way to find each other's current address automatically. And that is what a service registry does. And the way it works is two simple steps. When a service starts up, it registers itself. I am the payments service and this address. And anything that needs payments asks the registry for the current list and gets fresh addresses back. The registry also health checks them. So anything that has died drops off the list automatically. So, in our store, at large scale, we split into services like orders, payments, and inventory behind an API gateway. So, different teams can move independently. But the moment you have many services talking over an unreliable network, failures become normal. So, the next concept is all the techniques we use to survive those failures gracefully. Okay, in a big distributed system with many services over an unreliable network, failures are normal, not rare. So, a big part of system design is a set of patterns to survive those failures gracefully. Let's go through the four worth knowing. A note on this, the specific algorithms like the token bucket are really prepped for a design a rate limiter question. In a general design interview, it is enough to say that you would rate limit and why. The first is rate limiting. This protects your system from too many requests, whether from one aggressive user or a bad script or an attack. A rate limiter simply caps how many requests someone can make in a given time, say 100 per minute. And once they cross it, it rejects the extra ones with a status code 4 to 9 too many requests. And the main mechanism to know is the token bucket. Picture a bucket that is refilled with the tokens at a steady rate, let's say 100 per minute. Every request takes one token out, and if the bucket is empty, the request is rejected. And because unused tokens collect in the bucket up to its size, a quiet user can suddenly make a small burst of request, which is usually exactly what you want. The leaky bucket is a close cousin that smooths the rate out instead. So, rate limiting keeps any one source from overwhelming you. The second is idempotency, and this comes straight from our queue discussion. Remember, a message or a request can arrive twice. The network is unreliable, so clients retry. Now, imagine that request was charge the card. If you process it twice, the customer is charged twice. A disaster. Idempotency means an operation can be safely repeated with no extra effect. The standard trick is an idempotency key. The client attaches a unique ID to the request and the server remembers I already processed this ID, so a repeat just returns the first result instead of charging again. So a safe retry never double charges. The third is retries with backoff. When a call to another service fails, often the right move is to just try again. It might have been a brief blip, but if you retry immediately and forever, you can make things worse. Thousands of clients flooding a struggling service. So you use exponential backoff. Wait a little, then double the wait each time, and add jitter, a little randomness, so that all your clients do not retry at the exact same moment and stampede together. Retry, but politely. And the fourth is the circuit breaker, a really elegant one. Imagine one service your stores depends on becomes very slow or starts failing. If you keep calling it, your request pile up waiting and your service goes down as well. The failure spreads. A circuit breaker prevents that. It works exactly like an electrical fuse with three states. Normally it is closed, calls flow through. But if it sees too many failures, it trips to open. And now it stops calling that service entirely and fails fast, giving the sick service room to recover. And after a while, it goes half open. It lets a few test calls through, and if they succeed, it closes again. Closed, open, half open. And the two numbers that make it a real machine. Too many failures is a rule you set. Something like if more than half of the last 20 calls failed, trip. It is always measured over a recent window, not a lifetime total. So old failures do not count forever. And after a while is just a timer. Let's say 30 seconds before it lets those test calls through. This one stops a single failing service from taking down the whole system. So, in our store, rate limiting, idempotency, retries with backoff, and circuit breakers is what keeping the whole thing standing even when individual parts misbehave. Okay, we have now designed the entire system. The last big area is how you actually run in real world, how you package it, ship it, and watch it. And that starts with containers. Okay, we have many services, each needing to run on many machines. And a classic, painful problem shows up. The code runs fine on the developer's laptop, but breaks on the server because the server has a different setup, a different version of something. The famous line, but it works on my machine. So we need a way to package a service with everything it needs so it runs identically everywhere. And that is a container. A container, and the popular tool is Docker, is a lightweight standard box that holds your service plus every dependency it needs, the right versions of everything. And because the box carries its whole environment, it runs exactly the same on a laptop, in testing, and in production. And one honest note before we go on, containers and Kubernetes are not really system design interview material. They belong to DevOps interviews. And in a design interview, leading with I would use Kubernetes actually counts against you. But you genuinely cannot understand how a real system runs without them. So let's do them properly. And the first thing to get right, a container is not a virtual machine. A virtual machine runs a whole separating operating system which is heavy and slow to start. A container shares the host machine's operating system, so it is far lighter and starts in seconds. And what does isolated actually mean here if they are all sharing one operating system? The operating system gives each container its own private view, its own file system, its own list of running processes, its own network address, so it cannot see or touch anything else on that machine. And it also puts a limit on how much CPU and memory that one container may use. So a busy container cannot starve the others. So the box carries the libraries and files your app needs. It does not carry an operating system of its own. It borrows the hosts, and the host keeps everything in their own lane. Now, one container is easy, but a big store runs thousands of containers across hundreds of machines, starting them, restarting the ones that crash, adding more when traffic rises, spreading them across machines. Doing all that by hand is impossible. So, you need a system that manages them for you, and that system is Kubernetes. Kubernetes, often written K8s, is an orchestrator. It runs and manages your containers across a whole fleet of machines, and its core idea is genuinely elegant and worth stating clearly. You declare the desired state. For example, I always want 5 copies of the order service running, and Kubernetes constantly works to make reality match that. It is exactly like a thermostat. You set the temperature you want, and it does whatever it takes to reach it. So, if one of your 5 containers crashes in the middle of the night, Kubernetes notices and starts a new one immediately. So, this is called self healing. It If traffic spikes, it can start more copies, auto scaling. and it can roll out new versions gradually. And one more honest note, most small projects do not need Kubernetes. It is powerful but complex, and it is only worth it once you truly have many services at scale. Reaching far too early is a very common mistake. So, in our store, containers package each service to run identically everywhere, and Kubernetes runs and heals thousands of them without a human watching. Now, we can package and run our services, but how do we ship a new version of the code safely without taking the site down? That is our next step, CI/CD. Okay, so our code is written, packaged in containers. Now, how does a new version actually get onto the live servers safely and ideally many times a day? Doing this by hand is slow and dangerous. So, teams automate the whole thing, and that automation is called CI/CD. Let's split the two letters. CI is continuous integration. Every time a developer makes a change, it is automatically built and tested right away. So, bugs get caught within minutes, not weeks, and the code is always in a working state. And CD is continuous delivery or deployment. That same tested changes then flows automatically out to the servers. Together, they form a pipeline. Code, then build, then run the tests, then deploy automatically every time. Now and again, CI/CD is DevOps territory rather than a system design interview topic, but it is how every real system actually ships, so it is worth knowing. The interesting part is how you deploy a new version without downtime. There are three standard strategies. The first is a rolling deployment. You replace your servers with a new version a few at a time, so the site stays up throughout. A second is blue green. You keep two complete environments, blue running the current version and green running the new one. You test green fully, then switch all traffic over in one stint. And if something is wrong, you switch straight back. And the third, the safest, is a canary deployment. You release the new version to just a small percentage of the users first, say 5%. Watch closely for errors, and only if it looks healthy do you roll out it for everyone. And the single most important safety net, rollback. If a new version turns out to be bad, you must be able to instantly go back to the previous, known good version. A good deployment system makes rollback fast and reliable, which is exactly what you want when something breaks in the middle of the night. So, in our store, CACD lets us ship improvements many times a day, safely using strategies like canary releases and rollback in seconds if something goes wrong. Now, our system is built, running and updating itself. But with hundreds of services, one final question remains. When something does go wrong, how do you even see it? That is observability. Okay, our store is now hundreds of services across thousands of containers. And one day a user says checkout is slow. Now, where do you even look? You cannot open each of a hundred services and read its memory. So you need to build the system so it can explain itself. And that ability is called observability. And it stands on three pillars. And a useful note here, in interviews, observability usually shows up as a design prompt, as in design a monitoring system rather than as theory you get quizzed on. What does get noticed is simply that you think about how the system is watched instead of ignoring it. The first pillar is metrics. Metrics are just numbers over time. Request per second, error rate, average response time, CPU usage. They answer the question, is something wrong? You put them on dashboards and you set alerts. So if the error rate suddenly spikes, the system automatically pages an engineer. There is a well known set to remember called the golden signals. Latency, meaning the delay before a request completes, plus traffic, meaning how much demand is arriving, request per second, errors, meaning what share of those requests failed, and saturation, meaning how full your system is, how close the CPU, the memory, or the queue is it to its limit. And saturation is the interesting one because it warns you before things break, while the other three tell you it is already breaking. Metrics are your early warning that something is wrong. And closely tied to metrics is a framing worth knowing, availability targets. The SLO and error budget vocabulary below is really SRE territory, not system design. But how many nines does come up when you state your requirements? You will hear a system described as 3 nines or 4 nines. That just means 99.9% or 99.99% uptime. And the teams set an SLO, a service level objective, a target like 99.9% of requests should succeed, while an SLA is an actual promise to the customer, often with a refund if you miss it. And there is a clever idea on top called error budget. If your target is 99.9%, then that remaining 0.1% of failures is your budget to spend. As long as you stay within it, the team is free to ship fast. So nines, SLO, SLA, and error budget, those four come up again and again. The second pillar is logs. A log is a detailed timestamped record of individual events. User 42 tried to check out. Payment failed with this error. Log answers the question why did it break? The detailed story. And the key practice, logs should be structured and tagged with a request ID. So you can filter all the log lines for one specific request across the system. Unstructured just means the log line is written as named fields, user ID, order ID, status, duration, instead of one English sentence, because a machine cannot reliably search sentences, but it can search fields instantly. And all those lines are shipped off the individual machines into one central system, which is what lets you search across hundreds of services in one place. And one rule you should state out loud: never log secrets, no passwords, no card numbers. And the third pillar, the one people completely forget, is tracing. Remember, in microservices system, a single request might hop through a dozen different services. A trace follows one request across all of those services, showing how long it spent in each. So it answers the question, where in this whole chain did it get slow? It works by attaching a unique trace ID to the request, which is passed along to every service it touches. So you can stitch the whole journey back together. And how does that stitching happen? The trace ID writes along in a header on every internal call. So all 12 services see the same ID, and each service separately reports its own little record. I had traced ID X. I started here. I finished here. And that piece is called a span. A collector then groups every span carrying the same ID, lines them up in order, and you see the full journey with the slow one standing out immediately. Metrics say if, log says why, traces say where. So, in our store, observability through metrics, logs, and traces is what lets us actually run this huge system and find and fix problems quickly. Now, there is one area we have touched on but not faced directly, and it runs through everything, keeping the store and its users safe. So, let's finish the building with security. Okay, our store handles passwords, personal details, and money, so security cannot be an afterthought. And the first thing to get crystal clear, because introduce test the confusion here, there are two different ideas: authentication and authorization. Authentication is who are you, proving your identity, like logging in. Authorization is what are you allowed to do, checking permissions like can this user view someone else's order. Logging in does not mean you are allowed to do everything. Auth N is identity, Auth Z is permission. Now, authentication starts with passwords, and there is a hard rule you must know. You never store passwords as plain text. Never. If your database leaks, every password is exposed. Instead, you store a hash of the password, a scrambled one way version that cannot be reversed back into the original. And one important detail, you use a deliberately slow hashing function built for passwords like bcrypt or argon2, and not a fast one like SHA-256, precisely so that an attacker trying to guess millions of passwords finds it far too slow to be worth it. And you add a random salt to each one, a bit of random data mixed in, so that two people with the same password still get different stored values. And the salt is not a secret, it is stored right next to the hash in plain. And that is fine. And it is also how login works. You take the stored salt, mix it with the password they just typed, hash it, and compare. The real point of the salt is that an attacker cannot guess one password, hash it once, and match it against a million stolen accounts with a different salt on each. He has to attack every account separately. When someone logs in, you hash their attempt and compare the hashes. And after login, you give them a session or a JWT, exactly as we discussed earlier. And you will hear OAuth. At high level, it is a standard that lets one app get permission to act on your behalf in another app without handing over your password. So, what actually happens when you click login with Google? Our store sends you over to Google. You log in there on Google's own page, and Google asks you, do you allow this store to see your name and email? If you say yes, Google sends your browser back to us with a short one time code. Our server then calls Google directly, hands over the code plus its own secret, and gets back an access token, basically a string that stands for that permission. And after that, our server calls Google's API with the token. So your password only ever goes to Google, and our store only ever holds a token, which can be cancelled at any time. And login with Google is built on top of it using an extension called OpenID Connect. So, a small, precise point worth getting right. OAuth itself is really about authorization, permission, and the actual login, the identity part, is OpenID Connect, sitting on top of it. Either way, your store never even sees your Google password, worth knowing by name. And encryption quickly in two places. In transit, data moving over the network is protected by TLS, the HTTPS we set up at the very start. And at rest, data sitting in your database and storage should be encrypted as well. So a stolen disk is useless. Encrypt both. And finally, three classic attacks worth being able to name with one line defenses. To be straight with you, this level of security detail belongs to a security interview, not a system design one. In a design interview, it is usually a single line about which endpoints need authentication. But you should still know these as an engineer. SQL injection. An attacker sneaks malicious commands into input field to trick your database. The fix is to never build queries by pasting user input, but to use parameterized queries. XSS, cross-site scripting. An attacker injects malicious scripts that run in other users' browsers. The fix is to carefully escape any user content before showing it. And CSRF, cross site request forgery. A malicious site tricks a logged in user's browser into making a request they did not intend. The fix is a secret token that only your real site knows. Name the attack, name the fix. So, in our store, security means proving identity, checking permissions on every action, hashing passwords, encrypting everything, and defending against the common attacks. And with that, we have actually built the entire system end to end. So, let's step back and see the whole thing together. Okay, let's put the whole picture together because this is what an interview really is testing. Not just the pieces, but how they fit. You open the store, DNS turns the address into server's IP. Your browser opens a reliable connection with TCP, secured by TLS, that is HTTPS. It sends an HTTP request. The big static files come from a CDN near you. The request hits a load balancer, which spreads it across many stateless servers. A server checks a cache first, and only asks the database which is replicated for reads and sharded for size if it has to. Slow work like emails is dropped onto a queue for workers to handle later. At scale, the whole thing is split into microservices, protected by rate limiting, retries, and circuit breakers, all packaged in containers, run by Kubernetes, shipped by CI/CD, watched by observability, and wrapped in security. And that is a modern website, end to end. Every single piece exists to solve one specific real problem. Being found, being fast, handling scale, surviving failure, staying correct, staying safe. And you now understand not just what each one is, but why it exists and how it connects to the rest. And honestly, this is exactly what a system design interview is checking. And it also the difference between using these tools and actually understanding them. And that part stays with you long after any one interview. And that is the whole series. Four parts, one complete picture. From a single request all the way to a running scaled production system. So go back through the concepts that felt shaky, say them out loud in your own words, and you will be well prepared. If this helped you, subscribe, and the full playlist is right there to revisit any part before your interview. Thank you for watching all four parts, and good luck.